Aloha. So today I'm coming to you from beautiful Hawaii. I decided to change the background. I was getting tired of that upscale kitchen or whatever my background was. So now my new visual of lies is Hawaii for now. So welcome to lesson 6. This is a good one. We actually get to the good stuff now. So we're into chapter 2. And we get to cover some fun things now. So chapter 1 was just going through the weeds of how do we analyze op amps, how do we analyze op amps more hellishly, how do we analyze op amps even more hellishly. And we're going to still sort of come back occasionally, right? Where necessary, we're going to come back to the concepts we talked about in chapter 1. But now we're basically getting into the nuts and bolts of how do we use op amps. Now this is how do we actually use op amps to do cool things. So I think it's a lot more fun now that we're in chapter 2. We get to start looking at some actual practical op amp circuits that do cool things, and we'll get to do them in lab as well. So where were we, right? So far we've looked at 4 basically different ways to analyze op amps. We have the ideal case, we have the analysis with, well, 3, I guess. Well, ideal case, we have analysis with finite gain. Then we have modeling the op amp as a feedback network. So we have a feedback model. And then we have the last thing we talked about was modeling it as a more complex feedback network that had feed through gain and also had the return ratio. So those are our different ways so far that we've talked about of modeling op amps. And we have to use different versions of those techniques depending on the sort of thing we're looking at. If we're looking, for instance, if we're looking at the impact of input-output resistance of the actual amplifier itself, that's typically where we would have a return ratio analysis that we would use. If we're just looking at generally how it behaves, then sort of an ideal assumption might be suitable. But occasionally as we go over this stuff, we'll pop back to one of those techniques we talked about. Moving forward, though, we're considering practical uses. So how do people actually use op amps? Specifically for this class, we're talking about practical uses for DC case. So basically, these are mostly resistive circuits. We're not really talking about op amps with capacitors and inductors, although occasionally we'll talk about capacitance as needed. Okay. So first thing, so we're going to get started. We're just going to start talking about how do you do different things. If you're given a current, how do you make a voltage? If you're given a voltage, how do you make a current? If you're given current to current, voltage to voltage, right? We've talked a lot about the voltage to voltage converters, but we're going to start going through just some. If you're actually trying to do this, what do you do? So what if you got a little tiny current? You've got a little tiny current, and you want to measure that current, or you want to have that current presented in a way that a microcontroller can read it, or some other analog to digital converter can read it. Usually you'd use a current to voltage converter. And these current to voltage converters are typically used for small currents. So if you have a big current with a fairly strong source, there's sometimes a lot of easier ways to do this sort of thing. But for a small current, for a small current, maybe a very non-ideal source to that current, you're going to want to use an amplifier circuit to boost that before you have your output go to some other system, something like an analog to digital converter. So here you've already basically seen this, but this is the basic current to voltage converter. Fairly straightforward. We talked about this, right? This was, what topology is this? This is the shunt topology. So again, we're sampling the output voltage, which is in shunt, and we are combining currents in shunt. So it's the shunt topology. We've spent a lot of time talking about this. And basically, we have some current I input, and that current I input flowing in here. We also have some current I feedback flowing in here. The sum of those has to equal 0. So basically, the feedback current equals negative the input current. And so the feedback voltage the out is going to be 0 plus R times IF. Oops. So our output voltage is negative R times this input current. Fairly straightforward. If we want to do a more complicated analysis of this circuit, a couple things to note. If we wanted to do a loop gain analysis, loop gain, yeah. If we wanted to do a return ratio analysis, this is our return ratio for this circuit. The open loop gain based on that is, the closed loop gain is negative R, attenuated by 1 over 1 plus 1 over t. And again, if we were just using a more simplistic, finite open loop gain, we could use L as well. We could use the loop gain instead of t there if we had solved for the loop gain, which is a little more straightforward. There's a couple things to note, and we talked about this last time. The input resistance, one thing to know, that output resistance shows up in the input resistance. So this actually happens a lot. This is probably the circuit where this is most critical. The reason it's critical is because a lot of times this current source you have for a real circuit is something that produces a very tiny amount of current. It's also sometimes something where you want to have this signal quickly change. A common example of using this circuit is if you a photodiode, which is used for, like, if you have like an infrared, let's say you have an infrared remote control and you have a TV that's receiving that signal from the infrared remote control. Typically on the TV side, it's going to have a photodiode where the photodiode produces a current proportional to the light intensity at the input. Well, those photodiodes are usually modulated, because if they weren't modulated, you'd be picking up all kinds of noise from outside and things like that. So they're usually, the signal sent by your remote control is it's modulated at a specific frequency, and that can get filtered out later, and you'll talk about that in the next class. But the signal that's coming in is usually going to be something that looks like this, right? It's going to be, and I think they're typically around 30 kilohertz or so is the modulation frequency of those signals, somewhere in there in the kilohertz range. And this can be a very small current. So it can be a teeny tiny, your remote control is maybe, it's probably putting out a pretty bright light, but you want your TV to still work if somebody's pretty far away. So there's only a very small amount of infrared light striking that photodiode. It's only producing a tiny amount of current, maybe nanoamps or less of current. Not only is it producing only nanoamps of current, but you want this nice sharp response. And so this output resistance, which this is actually output impedance. The output impedance, if there was capacitance here, if there was undesirable capacitance here, that capacitance shows up at the input. And then what you're going to see is basically your nice clean signal starts to look like this, right? So your input current is now unintentionally going to be charging and discharging this this Miller effect capacitance on the input of that. So that's the only thing. I had to find a reason to muddy up my slides, so I guess that was my reason. So okay, that's my main reason for showing that, just to remind everybody Miller effect is really important. Miller capacitance is really important. Okay, and then output resistance, which is RO divided by 1 plus T. So again, it gets cleaned up by a factor of 1 plus T when it's a shunt output. So shunt output divided by 1 plus T, or 1 plus L. Okay, fairly straightforward. But again, if you're amplifying a nanoamp current and you're trying to make a nanoamp current produce a volt, what does R have to be? Wait, this is a good time to stop. Have you do some work on your end. You have an input current, it's 1 nanoamp. You want 1 nanoamp input current to produce -1 volts of the output. What resistance do you need? Should be a fairly easy one, but pause the video anyway. If you're with people, talk amongst yourselves. Welcome back. So after about 5 minutes of you working on that problem, you probably got that if you have a nanoamp current and you need to convert it to 1 volt, you need the inverse of 1 nano, which is 1 giga ohm, or giga ohm if you're doing Back to the Future terminology. So 1 giga ohm resistor, that's pretty big resistor. Can you get it? Yeah, you can get a 1 giga ohm resistor. You can buy it, but what's a 1 giga ohm resistor? I am a 1 giga ohm resistor, right? This leather glove I have sitting next to me in the shed. This is probably a 1 gig ohm resistor. We have my notepad of some tape. This is probably a 1 gig ohm resistor here. You know, my point is made. A 1 gig ohm resistor is a very, very large resistance. So one thing we can do is if we don't want to use a gig ohm resistor, we can improve sensitivity with a T network. So we can improving sensitivity. I forgot. I made these slides a long time ago. I forgot I put Mr. T in there. That's funny. I just, you know, I laugh at myself in real time, but I really appreciate it when I put the effort to set up a joke for my own amusement days in advance. So we got Mr. T in there. So the basic idea is the same, right? I mean, the whole idea of feedback and op amps is the way you get bigger gain in an op amp system with feedback is to have greater attenuation in the feedback network. If you only allow 1/1000th of a signal at the output to come back to the input to be compared against your input signal, then your op amp is going to have to amplify it by 1 billion to make that 1 billion times 1/1 billion equal 1, right? So the way op amps, the way feedback works is the more you nuke a signal on its way back to the input, the greater the op amp will have to work to produce a large output. So how do we nuke a signal? So if we're sampling a voltage, how do we nuke a voltage? Well, in this case, right, we're sampling a voltage, we're converting it to a current with a resistor. That's what we were doing before. So before, essentially, we had, our output voltage, which was going through a resistor R, which then became a feedback current. And so again, if we want to have this feedback current be like 1/1000th, R would have to be 1 times 10 to the 9th. How else could we nuke it? How could we produce a feedback current that's really, really, really tiny without necessarily doing that? Well, one thing we could do is we could do something like this, right? We could, what if instead of doing a 10 to the 9th resistor, we just do a humble 10 to the 6th resistor. And then we basically down here, oh, look at what I did. Look at what I did. What if down here we do a little voltage divider and we make this our feedback? Not a voltage divider, sorry, a current divider. So basically we now want to split this and let's make this one like, I don't know. Let's make this one like 100 ohms and let's make this one like, or let's make this one 1,000 ohms. Let's make this one like 1 ohm. So now we have our current that got nuked by, our voltage got converted to a current, but it's not 1 billionth, it's 1 millionth. It's a humble millionth. But then ooh, I did this wrong. Then we're splitting it. So now we're splitting it. So basically, we have our current, that current, which was already reduced by a factor of 1 million, is now getting split, where what fraction of that current is going to be going through this 1,000 ohm resistor instead of the 1 ohm resistor? Well, I mean, ballpark about 1,000th of it is going to be going through there. And that's the idea behind a T network. The idea behind a T network is you convert a voltage to a current with some resistance, but then you also split that resistance apart. And the bulk of that feedback current you just throw away. The bulk of that feedback current you just send it out, send it off the ground, whatever. Don't worry about it. Throw it away. The whole point though is you're diminishing the feedback current as a way to effectively decrease the feedback gain without using a massive resistor. So we got, basically by doing this, we got a close. It's not exact. It's going to be a +1 off here, but we got close to 1 billionth reduction in the feedback without having, to use that massive resistor, that gig ohm resistor. So let's see what that looks like. So basically, so instead of that single resistor now, we have this T network, and you can see it's a T based on the positioning of Mr. T here. And we basically represent this, this is still a current converting circuit. And we basically just say, we still have this RI1, but now we have this additional term K. So we have this additional attenuation factor K, which is 1 plus R2 over R1 plus R2 over R. So what would it be in this case for these values that I just picked here? So for these values, this one would be R2. This one would be, our feedback would be R. And this one would be R1, yeah. And another way to think about this, by the way, is we produce a voltage divider between this resistor and this resistor. And then, so we divide the voltage with a voltage divider, and then we convert that voltage to a current using a resistance R, which is mathematically the way the R's are represented here is what it's doing, but you can think about it either way. It's two ways of choking the feedback current. So with this example here, plugged into this equation, we'd have 1 plus R2 over R1 is going to be 10 to the 6th divided by 1, which is easy, plus R2 over R, which is going to be 10 to the 6th divided by 1,000. So let's see what that is. I look like a binary result here. So we get, so our factor K here is 1,000,000 and change, right? 1,000,000, 1,001. You can pick better values if you want it to be perfect. But then that was multiplied by R. So now that's multiplied by 1,000. So times 1,000 was going to be just, let's make it even more binary, right? This looks fake. It looks fake. Put some commas in there. Okay, so basically 1 billion, right? We got 1 billion. So the gain of this amplifier is going to be negative 1 billion. But again, we only had to use mega ohm resistors or smaller. Okay, yeah, right? Why though? Why don't we want to use just a giga ohm resistor? Again, right? A giga ohm resistor is easy to come by. I got this glove right here is my giga ohm resistor. So why do we not want it, right? The easiest thing. Well, the reason we don't want to use giga ohm resistors is because basically everything is a giga ohm resistor. When you're actually physically building these circuits, you're going to be building them on a circuit board, and that circuit board has some finite resistance to it. And so if you're building a circuit that relies on resistances on the order of giga ohms, then you're going to run into this challenge of they're swimming in this parasitic giga ohm resistance. There's a couple ways to clean that up. So you'll notice in this circuit here, this is called a guard ring, but inside the guard ring, the circuitry, there's no green, right? There's all this green here. There's no green in this part of the circuit. That's because when they built this PCB, they specifically built it without solder mask. So the solder mask has some resistance that is lower than fiberglass. So all the circuits built on the fiberglass part of the board with no solder mask, because the solder mask had too low of a resistance, right? The solder mask was basically in parallel with these, with what should be big resistors. And so it creates an issue. So there's other reasons for that. You can have parasitic, so you can have noise come through. So if you have, giga ohm resistances swimming in giga ohm resistances, even thousands of giga ohms resistances, any signal on the board is going to produce a small voltage difference. Even if it's just 1,000th of your signal, that's going to be noticeable. So to avoid that, a lot of times we don't want to have big resistances. So we do tricks like the T network to avoid these sort of undesirable undesirable phenomena that result from us swimming in gig ohm resistances. If you really want to go crazy, you can literally cut holes in your circuit board. This is not an op amp, I don't think. DG411DY. I think that's like a rectifier or something. A lot of times, this sort of isolation shown here is used when you have like a voltage converter. So like a bridge rectifier on the front end of an AC to DC converter, a lot of times will do that just to keep the hundreds of volts away from the tens of volts. So, but that's an option too. If you're really worried about these stray resistance, if you really want to use a gig ohm resistor, you're gonna have to play games kind of like that. So, but they still pick up a lot of noise. They're still just not advisable. All right, so how do we use these? How do we use these current to voltage converters? A lot of times they're used for, anytime you have a natural, something you're sensing, something you're detecting in the natural universe where your detection mechanism produces a current as a result of this stimuli. Light is a very common one. So there's a lot of devices out there that when light strikes them, they either are able to conduct, or when light strikes them, they are able to sort of produce a small current. So either you can have some quantum mechanical based devices are photoconductive. It's very common. Photoresistors are kind of work that way. They're these sort of cadmium selenide. Anyway, it's basically just the current is able to flow when you're exposed to light. You also have photovoltaic effects, which is, things where the light striking the material actually generates energy. So the light striking the material actually produces a current at a certain voltage differential. The difference is photoconductive measurements generally have to be biased, because effectively this is just functions as a resistor. It won't produce current. It won't produce much current on its own. So you have to bias this so that exposure to light actually results in a current flow. Photovoltaic devices, typically you can just leave them be. You can just let them go, and they'll produce they'll produce their own current without a bias. Even with these though, sometimes adding a little bias helps. So sometimes people will still add a bias to photovoltaic devices just to get a little better performance. Sometimes you can get a little faster performance. It might be a little more noisy though if you add that bias. But anyway, that's kind of what people will do. This is very common. So anything that gets an IR signal, anything that receives a light signal, anything that does sensitive measurements is going to do something along these lines. There's other things, right? It's basically anything that causes conduction. So there's a lot of sensor devices that basically, when a chemical absorbs in the sensor material, it changes the current that flows through it. There's a lot of those sorts of phenomena. And so these types of amplifiers are quite common. What about voltage to current conversion? Well, voltage to current conversion, when's the time you would want to convert a voltage to a current? Well, one of the things is currents exist a lot in the natural world. Currents don't generally play that nice with voltage control devices like CMOS-based electronics. Generally prefer voltages as input-output signals to currents. And so usually it's easy for them to produce a voltage. It's easy for them to read a voltage. Currents, not so much. That's not always true, but usually not current. So if you're trying to generate a current that you can control with like a microcontroller or something, generally you have to have the microcontroller produce a voltage and then convert that to a current. Okay. So the voltage to current converter, fairly straightforward. You've also basically seen these before. So we can do this either in the non-inverting topology, which is, in this case, this would be a series. Sorry, in this case, this would be a shunt series. No, sorry. Series, and then this one would be a shunt series. So, Unless I got it wrong, and then I'm sure somebody will tell me. So thanks for that. Okay, but the basic idea is, in this case, you produce a voltage here. The op amp, it's sort of in the ideal case, is going to try to mirror that voltage up here. It's going to mirror it by producing a current. So the current that's required to mirror this voltage at the input here is going to be the current needed is VI over R. And then same thing here. This current flow here is VI over R. And op amp needs to produce that to zero out the terminal. Fairly straightforward. Okay. Oh, sorry. Getting sleepy here. So what about this? So in this case, basically, the op amp needs to produce a certain current and feedback to balance out these input terminals. And we're basically saying that, well, just stick the load in the feedback path. Stick the load in the feedback path, and whatever current the op amp needed to produce, that's all going to flow through the load. Boom. We're done. What's not so great about this? What's not so great about this is you'll notice that this load is what we call a floating load. That is to say, the terminals of this load are not set. Neither terminal of this load is set to ground. So some devices can do that, right? So for instance, if we're trying to drive an LED, and produce a current through the LED that's a function of this input voltage, then fine. You can put an LED in this load. This is going to work fantastic for that. But there's other things, like for instance, if we're producing a current which is a signal to another device, quite often that current signal is going to have to be it's going to have to flow. That other device is not just floating in the universe. It's expecting a current grounded, right? It's expecting a current flowing to ground. And so this won't work for that. So this is floating load. It's a floating load voltage to current converter. It's very straightforward. It's very popular, but it's only for times where your current drive is a device that can handle a floating load, something like an LED or a heater or something. This could do technically, I guess, if you're driving a heater with an op amp. Let's looking at the non-ideal effects of this, taking into account output resistance, taking into account the input differential resistance. Slightly different picture here, right? Slightly different. Our ideal is attenuated by this, and this is, I don't practically know why I put this up here. Take a peek, have the set of equations, know it, but this is just typically these circuits are not quite as sensitive as other circuits. Usually people are not using them in an application that requires absolute sensitivity. So yeah, it is what it is. Okay. What if though we want to produce a current to a grounded load? So we want to produce a current that flows through a load where one side of the load is connected to ground. That is a bit trickier. So for that, we need what's called a grounded load converter. Grounded load converter is shown here. You might notice, what do you see? Whoop, negative impedance converter. Our dear old friend, the negative impedance converter. So basically, we're going to use a negative impedance converter to produce a current flow through a load. We're not going to analyze this from scratch. I think there's a homework problem that does analyze this from scratch. We're not going to do it right now. Sorry, my watch. My watch thinks I'm doing. Oh my gosh. Oh my gosh, my watch thinks I'm working out. Sorry. I don't know why my watch thought I was working out. I don't know. Okay, so grounded load converter. My watch distracted me, technology. All right, so we got a negative impedance converter in here. So basically, we have inserted our negative impedance converter in our circuit. We have So if we do the, if we take our input voltage, do the convert, we do the if we do the source transformation on that input voltage to make a current source, we can model our circuit as shown here. Again, we just plopped in that negative impedance converter. Our load is connected here. Now, what do we know about an ideal current source? So we want this load to see an ideal current supply. But what does it mean to be an ideal current supply? It means what output impedance does an ideal current supply have? 0 or infinite? Infinite. We need to have an infinite output impedance in order for this to be an ideal current supply. So looking at this expression for RO, if we, oh man, I messed something up. Looking at this expression for RO, we have this equation here. I'm skipping the analysis for you here. I mean, you can do it. It's just resistors in parallel here. But looking at this analysis, what's going to make this infinite? What's going to make this infinite is when this term equals this term. So for this circuit to actually function correctly as an ideal output current flowing into our load, we need to make sure this ratio R2 over R1 equals R4 over R3. And when that is true, our output current is going to be our input voltage divided by R1. Now, notice R1 was in this ratio that had to remain equal. Oh, is that it? Whoa, quick one today. Okay, so when would you want to use a grounded load converter? Quite often you have, one time I see it a lot is you have industrial equipment that a standard for industrial equipment is a 4 to 20 milliamp signal. A lot of times you're trying to convert a voltage to a 4 to 20 milliamp signal. Grounded load converter is usually a great choice for that. So, and a lot of times, again, you don't always have access to both terminals. A lot of times you have two pieces of equipment, they might share a ground signal, but the output of your op amp is not going to be a two-terminal current output. It's going to be a single terminal with the anticipation that on the receiving end, they have that signal tied to ground. So the receiver is going to have to take care of that part of it. You're sending them one signal. It's going to be that 4 to 20 milliamp signal, which is sort of one of the industry standard signal conventions. So, but this is neat. I mean, I love grounded load converters. The one key thing though is this is critical. So this equality, as you start to get away from the ideal ratio here, and you can get away from this ideal ratio just by having non-ideal resistors, right? Resistors are maybe at best 1% accurate. So if you have a 1% error here, and these resistors are all sort of in the same sort of ballpark, it's very possible to have a fairly non-ideal output resistance. So balancing this is pretty critical to having this function correctly. Because even being a little bit off, op amps are generally very good at producing very close to ideal outputs, because the non-ideal effects, we can always improve them by a factor of 1 plus the loop gain, or 1 plus the return ratio. And so, if you have a million, if you're improving something by a factor of 1 million, that's fantastic. But you're never going to have you're never going to be able to buy resistors with an accuracy of 1 millionth, or maybe you could. You're going to be spending a lot for that. So it's a very important consideration that when you're using a grounded load converter, usually you have to build these with some sort of trim functionality. You have to have some way of having like a variable resistor, having temperature corrected resistors that allows you to dial this thing in perfectly so it actually functions properly as an output current. Okay. And that does it. That does it for today. Thank you for watching. I hope these are a little more fun. We're actually talking about actually doing things with op amps. Usually that's kind of what breaks people out of their, I hate this class, I hate this book, I hate everything. So come and join me. Aloha in Hawaii. I have this beautiful palm tree behind me. Nope, other side. Nope, other side. Oh, beautiful palm tree. I'm going to take a coconut. It's like pina colada. It's great. I'm not even sure if that's a coconut palm tree or whatever. I don't know. Everything magical comes from palm trees. So thanks for watching, everybody. I'll see you later.